Chapter 1 Algebraic Methods, the Section 1 Proof by Contradiction. So, we are going to prove mathematical statement by using contradiction techniques. So, contradiction is a disagreement between two statements. So, we'll work with the example and we'll get an idea. So, I'm going to use example 1 and we'll discuss with the example 1. In the example 1, uh, the example is given prove by contradiction that there is no greatest odd integer. So there is no greatest odd integer. So this is the original statement. This is the one we have to prove. So first of all, we have to get an idea what this statement says. There is no greatest odd integer. When we take a number line, 0, 0, 1, 2, 3, 4, like that, and we can go up to infinite. So those are odd integers, 1, 3, 5, then 7. Likewise, we can write odd numbers up to infinity. That means there are infinite number of odd integers. If you tell me any odd integer, I can tell that the next odd integer. So likewise, this is continuing, and if you tell one odd integer, I will tell another one. So until our life is finished, we can continue like that. So there is no greatest odd integer. If you tell something greatest, I can tell the next one. So then there is no greatest. So that is the idea. Now this is the one we need to prove this one. So having this knowledge, so this is the original statement. So the next step is to prove using the contradiction. We want assumption. We want to assume this original statement is not true. So that is false basically. So this is called a negation of the original statement. I'm going to write bit below this one. Negation of the original statement. So what is the negation of this statement? There is no greatest odd number, odd integer. So we know that that is true. Then we assume the negation. What is the negation? There is a greatest odd number, odd integer. There is a greatest odd integer. Let's take that is n. Then here we'll discuss another one. Assume original statement is original is I wrote in a simple way. This is not a acceptable way, but to keep the space, original statement is if n square is even, then n must be even. So what is the negation of this statement? The negation is if n square is even, then n must be not even. Then n must be not even. So we can write decently not even mean what? Odd. N must be odd. And another one, original statement. So original statement is square root 2 is an irrational number. What is the negation of this? Negation is square root 2 uh, is a rational number. Square root 2 is a rational number. We'll discuss another one. So the original statement is there are infinitely many prime numbers. Is this true? Yes, when you get the number line, so 1, 2, 3, 5, 7, likewise up to infinity, uh, we can explain it. Mean there are infinite number of prime numbers. There are infinitely many prime numbers. That is true. Now we want to write the negation of this one. So that is the assumption. The negation of the original. So what is the negation? There is a finite number of prime numbers. There is a finite number of prime numbers. So this is the algorithm. I mean the steps. The original statement, we have this one. Then we have to assume the negation. What is the negation? There is a greatest of number. So this is the setup we need to follow. Then we have a mathematical argument, and we will come to a different statement. We'll discuss with this example. Another original statement. If AB is irrational number, then at least one of A or B irrational. So what is the negation of this statement? If AB is an irrational number, then neither A nor B is irrational. If AB is irrational number, then neither A nor B is irrational number. So now I believe you have an idea about what is the negation. So a statement writing mentioning that the original statement is false. So we'll read again one more time to get the sense of this one. If n is even, then n must be even. So that is the statement. Negation is if n is even, then n must be not even. Not even mean odd. So original statement is square root 2 is an irrational number. So how do we write the opposite of it? Square root is a rational number. There are infinitely many prime numbers. There is a finitely numbers of prime numbers. Finitely, there is finite number of prime numbers. If AB is irrational, is an irrational number, then at least one of A or B irrational. If AB is irrational, one of A or B irrational. Then we want to write if AB irrational, no one is irrational. If AB is irrational number, then neither A nor B is irrational. Now we'll work with this example. So now this is the original statement. Now what is the assumption? So we have to write the negation. There is a greatest odd integer, will take, that is n. Now we want to give the mathematical argument. Now this is the mathematical argument. We'll understand this one first. So there is a greatest odd number. So we'll take now this is the number line. There is a greatest odd number. Let's assume that is maximum odd number is n. And there are other numbers, but there are no more odds from there. So this is the last odd number. Then what will happen? This is n is odd number. Then I will add 2 to this odd number. So 2 is even. And when you add to 2, there is another one. That number is called n plus 2 number. So is this n plus 2 number is odd or even? Now assume in this number line, so I am telling 5 is the greatest odd number. Then there are no more odd number greater than 5. Then you take 5 and then 5 is odd number. Then you add 2, that is even. When you add odd and even, what do you get? You know that when you add to odd and even number, you will get odd number. So that is 7. Then 7 is a odd number. So then I said 5 is the greatest. No, there is 7 greatest now. It means my statement is contradict. I say there is a greatest odd number, that is 5. Now you show me that there is a 7. Same as you had. I am telling that the greatest odd number is 52. Then what do you? So then there is a greatest odd number 52. Then you write, sorry, odd 52 is not odd number, 51. So write 51. So this is odd. Then you use a technique. You add 2. So that is even. When you add odd and even, what do you get? The odd number. What is that numbers? 53. Now you show me that you said 51. I said 51. You show and there's a 53. So this is more than 51. So then 51 can't be greatest. 53 is there. Likewise, I will tell something, you prove. I will tell something, you prove. Likewise, until our death life is finished, we can continue. So we will tell this argument in terms of n. So n plus 2 is n is odd number. Then you are using a technique to add 2. Then odd plus even make what? Odd. So then n plus 2 is odd. So that is the argument we want to tell. So there's no greatest odd integer. There is a greatest odd integer. How about n plus 2? This is n plus 2 greater than n, and n plus 2 is odd. Why? Because n is odd and 2 is even, then n plus 2 is odd, because odd plus even is odd, or odd plus even equal odd. So we have to write this argument with the proper wordings. So now n plus 2 is an integer greater than n. N plus 2 is odd as odd plus even is odd. Hence there exists an odd integer greater than n. Now there are two statements. There is a greatest odd integer. There is a greatest odd integer. So that is n. Now we prove that there exists an odd integer greater than n. Now these two statement, what will happen now? Disagreement. So now it's contradict. Then why it is contradict? Because our assumption is wrong. Hence, only possibility there is no greater or integer. That's all basically. So I'll write the rest. So this contradicts the assumption that the greatest integer is n. Therefore, there is no greatest or integer. So we prove this one. Hence, therefore, there is no greatest or integer. So you can read the example 1 in the book as well. Example number 2. Statement: if n square is even, then n must be even. So the assumption. So you want to give the negation. If n square is even, then n is not even. So n is odd. First of all, a little bit discuss what is the idea behind it. If n square is even, then n must be even. For example, 4 square. Do you think this is even or odd? Even. Then 4 is even, which is true. If 6 square, is this even number? Yeah, 36 is a even. So this is 16 is a even number. So 36 is even. Then 6 also even. If n square is even, then n also even. We don't know what is n, but we know that when you square this number, we will get a even. So this will imply that then n also should be even. That is the idea behind it. There exists a number there exists a number n such that n square is even, but n is odd. So in here, are we worrying about n square or n? We are worrying about n. We are going to tell something about n by looking at n square. My worry is n. So I'm going to tell something forecast by looking at n square. So this is the assumption negation. There exists a number n. So we are worried about n such that n square is even, but n is odd. So this is the negation. Now we have to give a mathematical argument. We'll do a bit sketch. This is even, odd. So n square is even, n is odd. That's what the assumption negation. N, any n number we can write 2k plus 1. Any even number we usually write any number in number line 1, 2, 3, 4, 5 like this. When you double this one 2, 4, 6, 8, 10. So doubling mean the number line we turn it into a even. So then we double this one 2n. So we'll take any odd number k. So any odd number, let's say k. So k is somewhere here odd. So I'll make this odd to even or double 2k. Then I'll take 2k. And I know that when I add to a even number plus 1, it is going to be odd. So I'll create now odd number 2k. So I get a number 2k plus 1 odd number. And now I square it. So this is n. So I will square it. I need n square. So It means 2k plus 1 square. What is the answer? 4k square plus 4k plus 1. So I will factorize 2. This is 2k square plus 2k from 2, and this is plus 1. It doesn't matter. This is a number. When you double by 2, it doesn't matter odd or even. Right? When you double, it's become even. And when you add plus 1, it is become odd. Now you can see that you take 2k plus 1 odd number, you are expecting that is be even. What will happen instead of that? It's become odd. So it is a contradiction. So I will write now. So n is odd. So we can write any odd number as 2k plus 1 is element of z, the integers, and then we can tell that n square equal 2k plus 1 square, which is 4k square plus 4k plus 1, 4k plus 1, then 2 times I take 2 out, so this is 2k square plus 2k plus 1. Then you want to tell 2k square plus 2k can be odd or even, but 2 times 2k square plus 2k is even. Hence 2 times 2k square plus 2k plus 1 is odd. Hence, what is this one? N square. We write n square. N square is odd. This contradicts the assumption that n square is even. Hence, if n square is even, then n is even. Let's discuss example 3. So example 3 is square root 2 is an irrational number. The assumption, we have to write the negation, the false of this statement. So square root 2 is a rational number. What is rational and irrational? Any number, if you can write as a fraction, we write fraction p divided by q, then it is rational. Any number we cannot write p over q as a fraction basically, then irrational. So that's simple. That's all basically. Now 4 is rational or irrational? You can write 4 over 1 rational. If we consider 3 over 5, yes, rational. Already it is in p over q form, rational. And but there are some numbers. For example, if this is a square with one side 1 and this length is square root 2. So you can write this as a rational number. There is no p over q exists for this. And the number is pi. This is we can give approximation 22 over 7, but we can't write this just approximation. You may work with 22 over 7, but just approximation. Usually 5. You can't. It's a irrational number. E Euler's number, and the golden ratio, um, and some other um, square roots. So basically, we can't write any number. We can't write as a fraction. So they are irrational. If we can, it is rational. Let's sketch our argument. Square root 2. So with the statement, we'll tell that square root 2 is we can't write square root 2 is a over b. A is a real number and b is a real number. But in the negation, we take that square root 2 is a we can write that. So we'll forget about this one. The negation, we will tell that square root we can write in a of b which as a fraction. Now also we can write as a fraction. Also we write they are in the simplest form. That mean you can't simplify any further. For example, 4 you can write 4 over 1 or 40 over 10 or 400 over 100. So now it is in the simple form. This one 4 over 1. Another one 2 over 6. 1 over third. We'll take half. Half we can write 2 over 4. So many ways. 3 over 6. 100 over 200. So in the simplest form, so it is in this form. So we assume that a and b we can't further simplified a over b. And we are going to show that this term can be further simplified. Now, this is the argument. So I will write a equal square root 2b. I just cross multiply. Then I will find a square. So this is going to be 2b square. It doesn't matter whatever be. When it's there are 2 times, we know this is even number. So then what we can tell, a square is even. If a square is even, then what you can tell about a? A also even. From example 2 we discuss if a square is a is a. A is even. Any number even, then I can write a equal to alpha. Or instead of alpha I will put 2 f another number in the real number. I tell that a is 2f. Now I will take this one again. A square equal to b square. Now a is 2f. So I will substitute that even number to here. 2f square equal to b square. This is 4f square 2b square. Then this is 2 divided by 2, b square equal to f square. What you can tell about this one now? It doesn't matter f square what it is, but 2 times f square is even. Then it means that b square is even. How can you write any number now? B square is even. So from the example 2 we discussed, if b square is even, then b is even. Then b you can write as 2 times t. T another number in the real number. Then what a divided by b? So a divided by b is 2f divided by 2t. So 2 times f over t. Oh, this is, I will stay with this one. What do I wrote? So 2 to 2 cancel out, f divided by t. We said it is in the simplest form, but it's not. So we wrote in f over t form. So it is contradict with this as our assumption. Yes, it's true that f over t is a fraction. We agree with that, but we don't agree with this one. It's not in the simple form. We managed to find another one. So why this happens? Because our assumption is wrong. Square root is rational number. It cannot be. Square root should be an irrational number. So we have to write this argument now. So square root 2 is a rational number. Hence we can write square root 2 as a fraction a over b. Uh, a is the element of r and b is the element of r real numbers, and fraction cannot be reduced further. So now we start the argument. Now you can write the proof. So this is the proof start. Then we cross multiply a equals square root b. This is 1. We'll square it. 1 square. A square equal to b square. So now we have to tell b square or 2b square is even. Doesn't matter b square even or 2b square is even. Hence a square is even, right? Hence we can tell that if a square is even, a is even. From example 2. Now then we know that a is a multiple of 2. So I'll write a equal to f is an element of real number again. Now I wrote a as 2f. Now I'm going to substitute a equal to f to equation 1. So part 1 is done now. So from equation, actually I'll take this is to equation 2. So a mean now 2f square plus 2b square. So 4 square is 2b square. So b square is 2f square. So I'll write b square equal to f square. So 2f square is even. Hence b square is even. Hence from 2 b is even. We know if b square is even, b is even. Hence b is even, we can write as a multiple of 2. 2 times t, t is a element of real numbers. Now I have B, A and B in hand. So I will take this is as 3 and 4. So 3 divided by 4, A divided by B equal 2F divided by, this is T, 2T, which is F over T. So it violates what we said. We said that the fraction cannot be reduced further, but we did. So now it is contradict. Then you can conclude, hence factor AB can be reduced further. Now this is a contradiction. Hence this is a contradiction to the statement that A over B cannot be reduced further. Hence, hence square root 2 is rational, irrational. So this is one way. You can simply change this one. If we can add uh, cannot be reduced further, there is no common factors between A and B. So this means that what? There is no common factors between A and B. So that is the idea behind it. Then you do this one and you will come and so you will tell that A equal to F. So and then we work out B square is even. So we will tell that we don't need so A square is even and A is even. It means there is a factor 2, right? And then hence B square even, then B is even. So we are not going to do any division or anything. Then we will simplify. We can give this way. Um, so we said this is even and this is even. Then that means that there is a common factor. So previously I did work one more extra step ahead. So you can conclude that now we tell that A is even, B is even. If A and B both even, then there should be a common factor. So the fraction cannot be reduced further. It means there is no common factor. That is the hidden hidden meaning behind it. So if A and B are both even, then there should be a common factor. Common factor of 2. We saw that. Hence, this contradicts the statement A and B have no common factors. Therefore, square root 2 is irrational. Let's discuss example 4 now. Example 4, we want to show that this means there are infinitely many prime numbers. Are there infinitely many prime numbers? When you take a number line, so 2, 3, 5, 7, 11, so those are prime numbers. Are they unlimited or limited? Yeah, there are unlimited prime numbers. It means there are infinite many prime numbers. So then we want to show that there are infinitely many prime numbers. So our assumption should be there is a finite number of prime numbers. Yeah, it's a number of prime numbers. So we will assume that okay, it has a boundary. To prove this one, we should have this knowledge. In this number line, this can be divided into two. Either number is a prime number. Any number is this number line prime number. If it is not prime number, it is composite number. So any composite number you can write a multiple of prime numbers. For example, if you take 6, you can write 2 times 3. So 2 and 3 are prime numbers. So composite numbers we can write the multiple of prime numbers. Another one, 42. 42 we can write, actually we did this one. 42 divided by 2 is 21. 21 divided by 3, 7. So 2 times 3 times 7, 2, 3, 7 are composites. 150 is not a prime number. 42 is not a prime number. 6 is not a prime number. 42 is a prime number. 150 is not a prime number. So then 75, 3, 25, 5 and 5. So 2, 3, 5, 5. They all are prime numbers. So number line can be divided into two categories, prime and non-prime, which is called composite. Any composite we can written as a using prime numbers. We can write as a multiple of prime numbers. So those are the two categories. Now what we are doing here, we are creating a number. Assume that we take the first prime P1, the second prime P2, third prime P3, and the last prime we want Pn. And so we are telling there is finite number of prime numbers. After that there is no prime. Assume like that. Or random selection. Assume that somewhere in the number line we have P1, P2, next one is P3 and Pn, and we found out the last one we have is Pn. Now I am creating another number. N is a number. Another number in this number line, N. And I am making with multiplying P1 times P2 times dot 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 P3 times dot 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 Pn. I multiply all the prime numbers. And so when I multiply all the prime numbers, and I will add 1. So it is a number in this number line. So this number can be either prime number. So if it is a prime number, the case is failed already. There is finite number of prime numbers Now we took that P1, P2, P3 up to Pn. But if you are going to tell that n also a prime number, then we found another number apart from this set. Then the case is failed. It is contradict. Hence there is so infinitely many prime numbers. Okay, assume now if n is not prime numbers, then it has to be composite. If it is composite, then P1 has to be a fact either P1, P2, P3, Pn or any combination. Actually, we know that we made this sum by multiplying all the numbers. Hence, we have only those prime numbers in our hand, and is P1 is a prime factor of this n. So P1 is not a factor of n, because when you divide n divided by P1, you can see that there is a remainder 1. So P1 is not a factor. How about P2? So can n divide by P2? Now P2 also not a factor, because if you divide n divided by P2, there is a 1 is going to be remain. Then P2 also not a factor. And P3 also same as not a factor. And everything including Pn also not a factor. Then, but this is, if it is composite, they should have a prime factor. Then our argument, there should be another prime number, let's say Pn, to become a prime factor of this one. So because of that reason, there is another, we found out another prime number. Because of that, there are infinitely many prime numbers, because it contradicts. There is finite number of prime numbers, because only we thought it is Pn, and we can't divide by P1, we can't divide by P2, P3, and we can't divide by the remainder. It's going to be, then there should be another one P. So this is the argument. So now we'll work on now list all the prime numbers that exist. We will list in P1, P2, P3, likewise Pn. Then consider a new number. Consider the number n. So n in this number line somewhere. So n is, we make this n by multiplying P1 times P2 times P3 times dot times Pn, and we add 1. Then we should have two possibilities of that. First possibility, n is prime. That is, n is prime. If n is prime, then we already found one more prime number apart from this list, that is n. The case is failed now, hence the assumption is hence there is other prime number is found that is n, which is not on the list p1 to pn. Hence, this is contradict with the assumption that there is finitely number of uh, finite number of prime numbers. The second option, the first possibility, second possibility, it should be a prime composite number. If it is composite number, we will be able to write this number as a prime, but p1, p2, p3 dot dot pn is not a prime factor of n, as they produce remainder 1 when they divide. Hence, there should be another prime number which is not on the list, which is not in the list. What is this list? P1, P2 to Pn. The second case also failed. Yes, this contradict with the assumption that there is finite number of prime numbers. Therefore, there is infinite number of prime numbers. There is an infinite number of prime numbers. In here, it is important that those steps, state assumptions, working out and show your contradiction, that it is contradict with the assumption, and then you have to write your conclusion. Therefore, there is an infinite number of, so you have to write the statement that you accept the statement. So those are 1, 2, working out 3, 4, and 5. Let's discuss the exercise 1A now.